All right, ladies and gents, so let's talk parametric curves. I have a table set up here. Before we jump in and use our table, we need to talk first about what these equations look like. And every set of parametric curves is indeed a set, which makes this differ a little bit from our traditional graphing situation, which you might have heard called rectangular curves or rectangular form of an equation. So here we have x equals t squared minus 4 and y equals t plus 1. And these curves work together to form these equations, I should say, work together to form a single curve given our parameter, which is t. So for the first time ever, we get to take a look at an actual xy position as a function of time instead of looking at just position as a function of time vertically or horizontally. And so if you took a look at just a kind of a generic graph, as you would graph a parametric curve through space, you would have these xy points. And each xy point would be happening at a certain time. So we would be plotting this as an x comma y point, but this might be at time equals 4. And then over here, you might be at this point at time equals 5. So this parameter of time is kind of happening in the background. So let's take a look more specifically at what this looks like for this example, which is x minus t squared, x equals t squared minus 4, and y equals t plus 1. First, I want to show you just sort of how we would plot these things. So they're done graphically with your times being just put in for t. So at -2, I get an x output of 0. And then -1, I get an output of -3. At 0, -4. You can see I'm just taking these times and just putting them in to my x equation. And 1 squared minus 4 is -3. When I put 2 in, I'm at 0 again, and then I'm at 5. And for y, the same thing occurs. This time I'm just going to use my y equation. I'll put -2 in, -1, 0, 1, 2, 3, 4. So graphically speaking, how does this look? Well, if I sort of put a little plot together here, I know I'm going to have to go over here, 3, 4. Scale my axis just a little bit, and this will be a little bit crude, but you'll get the picture. So x and y, and we'll use maybe red. So at time equals -2, and I just sort of chose an arbitrary starting point. So I'm plotting this for a time in between -2 and 3. As I start this thing off, I start at the point 0, -1. So 0, -1, so I'm down here. And then I need to move over to -3, 0. And then -4, 1. -3, 2. 0, 3. And then I jump all the way at time equals 3 over to the point 5, 4. So I'm up here. So you can sort of see this curve sort of moves around that way. And this actually has an orientation to it. And this shows sort of the direction. These arrows show the orientation or the direction that this curve follows as time progresses, as this thing moves kind of around in that curve. This means that, for example, at this point here, which was the point 0, 3, I achieved that point at time equals 2. So these two curves sort of work in conjunction with one another to form a single curve. Now, the cool part about this is that you can actually eliminate the parameter to see what this curve might look like if it were a single rectangular curve. So I'm actually going to come over this way so we can keep these on the screen. We'll go to blue. So I have these two curves. Now, to eliminate the parameter, I need to solve one of them, typically whichever one's easiest, works well, for time. So I'm going to take y equals t plus 1, and I'm going to subtract 1 from both sides. So I get t equals y minus 1. Now I'm going to take this t minus 1 and just substitute this in for time. So x equals y minus 1 squared minus 4. So here's my relation. And notice that this is not necessarily a function, but my original parametric curve set wasn't a function either. Right? If I look at this graphically, that is truly not a function. In fact, I could take this thing, I could load up a Desmos graph, and I have x equals y minus 1 squared minus 4. And look at that, it goes through all the same points as I did before when I graph this as a set of parametric curves. So there I eliminated the parameter. The other thing you can do is if you start with a rectangular or traditional function, and I'm going to start this in rectangular form this time, I can actually insert, right, a parameter or find a set of parameters that works for this function. So for instance, I could just say, well, x equals t works, and if x equals t, then y equals t squared plus 3. I could also say that x equals root t, and if x equals the square root of t, plugging that in, I get y equals just t plus 3. Now the kicker here is that you have to be really careful with your domain. So the domain for this particular time is limited. I can only put in values at 0 or greater. However, my original rectangular function did not have a limited domain. So this set of parametric curves would produce a different graph than this set of parametric curves, which would be the same as my original rectangular curve. All right, so a little bit of an intro into parametric curves, what they look like graphically, and how to kind of think about them. Take a look at the next video if you'd like, where we talk about the derivative of parametric curves.